So imagine you're a scientist
Right.
and you just discovered something that completely, rewrites the biology textbooks.
Oh, the dream scenario.
Right. You're right. You've like looked at the world, you've seen something totally new, and you have the data.
Right.
But uh, how do you actually get the rest of the world to believe you?
Yeah, you can't exactly just shout, I'm right from a
Ru-
mountaintop.
Exactly. Raw scientific data on its own is basically just, well, a pile of loose lumber and scattered nails. It doesn't really mean anything until you build it into a structure that can, stand up to a hurricane of skepticism.
Yeah, that's the perfect way to frame it because the pile of lumber is totally useless without a blueprint and a hammer to actually assemble it.
Right.
And in science, that blueprint and hammer is the claim evidence reasoning framework, or CER. It's basically the architectural standard for how scientists actually build an argument.
It was exactly why we're dedicating this deep dive to a very specific group today, seventh grade life science students and their teacher.
Shout out to the seventh graders.
Yes. So our central question for today's deep dives is basically, how do we move from "I think this" to "the evidence supports this explanation"?
Which is a huge leap.
It is.
Yeah.
We're going to look at how real-world climatologists and engineers and biologists construct knowledge, right? Rather than just sort of passively receiving it.
Yeah, and to the seventh grade scientists listening, I mean, we know you've probably seen CER presented as like a rigid paragraph formula or, one of those three-box
The
worksheets.
dreaded worksheets.
Right, but today we really want to pull back the curtain on why this framework is actually a living, breathing process. I mean, it is literally the mechanism by which human beings figure out the universe.
Okay, so let's just jump right into it. Let's start with the first structural pillar, which is the claim.
Right. So a claim is a clear, specific answer to a scientific question. But to really understand it, we kind of need to establish what it's not.
Okay, what is it not?
Well, a claim is not just a general topic. It isn't a personal preference. It's not a random observation. And it's definitely not a wild guess.
Right.
It's a declarative statement that serves as the conclusion you've drawn from an investigation.
Hold on, let me just push back on that for a second. If I make a declarative statement in science, aren't I basically saying, like, this is an absolute, undeniable fact?
No, actually.
Because what if a student runs a lab, makes a super confident claim, and then, realizes later they got it completely wrong?
See, that is a massive misconception, and it holds a lot of young scientists back because they are just, frankly, terrified of being wrong.
Yeah, nobody wants to be wrong.
Exactly. But scientific claims are not absolute truths handed down from on high. They are provisional.
Provisional, meaning they're, what, temporary? Like they come with an expiration date?
Kind of. They come with the understanding that they are our absolute best explanation based on the data we currently possess.
Right, right.
They can, and honestly, they absolutely should change when new evidence comes to light.
So it's not a failure if you have to change it.
Not at all. If you revise a claim because a new, better investigation provided conflicting data, that's not a failure. That is literally the definition of how science improves. It means you're doing the job correctly.
Oh, wow. Okay, that takes a lot of the pressure off, actually. You don't have to be perfect. You just have to be rigorous.
Exactly. Rigor over perfection.
Okay, so you've made this provisional claim. Now you need the lumber. You need the evidence.
Right, the gathering phase.
This is the information you use to evaluate your claim.
Right.
So we're talking observations, measurements, investigation results, graphs, models, that kind of stuff.
Yes, but, and this is a big but, this is where the filter really has to come in. Because not all information qualifies as strong scientific evidence.
Okay.
There are essentially 4 tests your information has to pass before it can actually be used to support a claim.
Okay, let's test this in the real world. Say we're investigating local ecosystems.
Okay, I'm with you.
And my claim is that deer populations in the local forest are thriving and increasing. And my evidence is, well, my uncle said he saw 3 deer eating his hosta plants in his backyard yesterday.
Oh boy.
Does that pass the 4 tests?
Let's run it through the gauntlet. Test number 1. Is the evidence relevant?
Well, he saw deer.
Right. Your uncle saw a deer, so it is at least connected to the topic of deer populations. We'll give it a very weak pass on relevance. Test number 2. Is it reliable?
I mean, he wears glasses, but his eyesight's okay.
Sure, but an anecdotal sighting by one guy in a suburban backyard is not a trustworthy, repeatable scientific method.
Fair enough.
It's not a standardized biological survey, so it completely fails reliability. Test number 3, is it sufficient?
Well, seeing 3 deer on one random Tuesday doesn't really show a historical trend, does it?
Exactly. Sufficient means you have enough data to establish a real pattern, not just a one-off fluke. One data point is an anecdote. It's not a trend.
So it utterly fails the sufficiency test.
Utterly. And finally, test number 4. Is it accurately interpreted?
Ah, I see the problem there. He saw deer in a suburban backyard. That doesn't necessarily mean the deep forest population is thriving.
Yep.
It might actually mean the forest is dying and the deer are starving, so they're forced to forage in human neighborhoods.
Precisely. You basically twisted a random observation to fit a preconceived notion without accurately interpreting the context.
So my uncle's hosta plants are terrible scientific evidence.
The worst. Good evidence has to be relevant, reliable, sufficient, and accurately interpreted.
Got it. Okay, so that brings us to the R, the reasoning, which, looking at the source material, seems to be where the wheels kind of fall off for most people.
Oh, absolutely. It is definitely the most cognitively demanding part of the whole process.
Why is that?
Because reasoning is the logical bridge connecting your raw evidence back to your claim. You have your lumber, the evidence. You have your blueprint, the claim. The reasoning is the hammer that drives the nails.
I like that.
It relies on accurate science ideas, mechanisms, cause and effect relationships, and, biological systems.
There's a quote in the research we looked at that feels like the ultimate golden rule for this entire framework.
Oh, I know the one.
It goes like this. Evidence tells us what we found. Reasoning explains why it matters.
Yes. Evidence tells us what we found. Reasoning explains why it matters.
I love that.
Okay.
Because if you only provide evidence, you're basically just handing someone a spreadsheet of numbers.
Right, just a data dump.
Exactly. The reasoning forces you to prove that you actually understand the underlying scientific mechanism.
Okay, let's put this into practice. Let's walk through the, aha moments of some actual scientific phenomena that 7th graders study in life science.
Let's do it.
We'll start at the microscopic level. Cells and living things. The guiding question is, why is a cell size limited?
A foundational biology question. So a strong provisional claim here would be something like cells must remain small to efficiently transport materials in and out of themselves.
Okay, so we need our reliable, sufficient evidence. We can't just look through a microscope and guess.
Students would actually look at mathematical surface area to volume calculations. The data shows this geometric reality, right? As a cell gets larger, its volume-like, the inside stuff increases way faster than its surface area, which is the outer skin.
Exactly.
So the actual mathematical ratios from the lab are the evidence.
But again, those ratios are just numbers on a page until we apply the reasoning. This is where you have to explain the biological mechanism.
The why.
Yes, the why. You bring in the concept of structure and function and you explain diffusion.
Because nutrients have to physically travel from the outside of the cell to the center.
Right. Think of it like, imagine a tiny microscopic city.
Okay.
If the city is small, supply trucks can easily reach the center from the highway. But if the city suddenly expands to the size of a continent and you still only have one highway on the outer edge, the supply trucks take way too long to reach the middle.
No, that makes sense.
In a cell, if the volume gets too big, nutrients literally cannot diffuse through the cytoplasm to the center fast enough, and the cell starves. Or, conversely, toxic waste builds up in the center and can't get out.
So you're bridging the geometry to the biology. But the sources point out a pretty huge pitfall here.
Yes, they do.
A really common student mistake is treating an opinion as evidence. They might write, like, small cells are just better for the body, or it's easier for them to fit together.
Which completely bypasses all the rigorous work.
Why do we think students do that?
I mean, because doing the math is hard.
Yeah, that's fair.
Stating a preference or a vague observation feels safer than risking an incorrect mathematical interpretation. But, as we know, an opinion doesn't pass the tests of strong evidence.
It really doesn't. Okay, now, if that mathematical limit dictates how a single microscopic cell survives, what happens when we zoom way, way out? Let's look at, say, billions of cells working together in a macro environment.
Like an ecosystem.
Yeah. Exactly. Like a deer trying to survive a drought. This brings us to resource availability in ecosystems. The question is, what happens to a deer population if rainfall significantly drops?
The claim is pretty straightforward. The deer population will decrease due to reduced plant forage.
And for our evidence, we can't just use my uncle's backyard.
No more hosta plants.
Right. We need a sufficient data set from a long-term study. The evidence would be specific data points like Rainfall dropped by 10 inches in year 3, and subsequently, the deer population plummeted from 500 individuals to 300 individuals in year 4.
Notice how specific that is. It isn't just it rained less and deer died. It's quantifiable.
Yeah.
But this leads to another major psychological trap.
Which
The
is?
common mistake here is listing that data without interpreting it. It is incredibly common for a student to just copy those numbers onto their paper and stop writing.
Data dumping.
Yes, data dumping. It happens because copying numbers feels safe. The numbers are objectively true, so the student thinks, well, I can't be marked wrong for writing this down. But just dumping numbers isn't an argument until you explain the mechanism.
You have to tell me why the lack of rain killed the deer. Because, the rain didn't fall on the deer and crush them.
Exactly. That's where reasoning comes in, using the scientific principle of cause and effect. You have to explain that rain is an abiotic factor, a non-living thing that acts as a limiting factor for plant growth.
Oh.
Plants are the primary producers. Less rain means less photosynthesis. Less photosynthesis means less chemical energy is available at the bottom of the food web.
Oh, I see where this is going.
Right. When that energy bottleneck happens, it starves the primary consumers higher up the chain, the deer. You are connecting the abiotic weather to the biotic population crash.
It's a total domino effect of energy transfer. Okay, let's look at one more example. We'll introduce the factor of time, traits, and natural selection.
Oh, classic.
The question is, how do environmental stressors affect population traits over generations?
Right, so let's look at the snowshoe hare. A solid claim would be, snowshoe hares with genes for seasonal color change survive predation better in environments with snow.
Okay, so our evidence would be data showing trait frequency shifts, like over multiple generations. An ecologist's data table shows that the percentage of white-coated hares increases significantly during winter months, while the brown-coated hares drop off dramatically because predators spot them easily against the snow.
The reasoning here is absolutely critical. You have to explain the mechanism of natural selection. The environment is acting as a filter, selecting for pre-existing genetic patterns. The hares whose genes naturally trigger a color change, well, they blend in. Because they aren't eaten, they live long enough to reproduce, passing that specific genetic trait to the next generation.
And here's the trap, and it's super fascinating because it's so rooted in human psychology. Students will often write their reasoning and say something like, this proves hares choose to change color so they don't get eaten.
Yes, the anthropomorphic bias. We are humans, so we just assume everything else makes conscious choices like humans do.
Exactly. But you can't just throw the phrase, this proves, into your writing without explaining the genetic why. Hares don't, wake up in November, look at the snow, and consciously decide to change their wardrobe.
They're not going shopping.
No. The reasoning has to explain that this is a random genetic variation being acted upon by environmental pressure.
It is so illuminating to explore why we fall into these traps. And, when you're staring at a blank piece of paper trying to construct an argument, there are a few more predictable pitfalls you really have to navigate.
Oh, totally. Let's troubleshoot them. The first one is basically cognitive stalling, which is repeating the question as the claim.
Oh, yeah.
A student will start their paragraph with, the question is about what happens to the deer. Why do we do this? Because facing a blank page is intimidating.
Very intimidating.
Restating the prompt feels like you're generating momentum. But in science, you just need to state your declarative answer directly. Skip the warm-up.
Another major pitfall is repeating the evidence in the reasoning section. You see a student write down their data, and then for reasoning, they basically just write the exact same data again, maybe adding the word because in front of it.
That goes back to the fear of the biological mechanism, right?
Yeah.
If you don't fully understand diffusion or energy transfer or natural selection, you just repeat the numbers hoping the data speaks for itself.
Exactly. But here's the secret. Data never speaks for itself.
Right.
The scientist must speak for the data, and I'd say the most dangerous pitfall of all is ignoring evidence that challenges your first idea. This is cherry-picking data to fit your own confirmation bias.
This one is huge, and let's be honest, it happens to professional scientists too.
Oh, constantly.
When you make a provisional claim, your brain gets attached to it. When an anomalous piece of data shows up that contradicts your beautiful claim, it causes cognitive dissonance.
It literally feels physically uncomfortable to be wrong.
It really does. So the temptation is just to sweep that one weird data point under the rug.
But sweeping data under the rug is the antithesis of science. If a piece of evidence doesn't fit your claim, You have two choices. You either have to explain the anomaly through a scientific mechanism, or you have to do the brave thing you have to revise your provisional claim.
I want to give the listener a visual for all of this.
Yeah.
Think of it like being a trial lawyer in a courtroom. You burst through the doors, you throw a muddy shoe onto the judge's bench. That's your evidence.
Okay. Dramatic.
Very. You point at the defendant and yell, "He is guilty." That's your claim. And then you just sit down and cross your arms.
The jury would look at you like you were completely out of your mind.
They would. You haven't proven anything. You have to explain how the mud got on the shoe, why the chemical composition of the mud perfectly matches the dirt at the crime scene, and how the unique tread pattern connects the suspect to the footprints outside the window.
That's the reasoning.
That intricate step-by-step explanation is your reasoning. Without it, you aren't a lawyer making an argument. You're just a weird person who put a dirty shoe on a table.
That analogy perfectly captures the stakes, really. It's about building an airtight case. And I want to zoom out to the broader applications here because mastering CER isn't just about, getting an A in 7th grade life science.
It's a foundational life skill.
Truly, it connects to every single scientific practice you will ever do. It's the framework you'll use to build computer models. It's how you'll analyze complex data sets in high school and college.
Yeah.
Even when you sit down for a portfolio reflection and have to justify your own learning journey, you are using claim, evidence, and reasoning to prove your growth.
But the stakes go even higher than academics, I think. It is ultimately about real-world decision-making. We live in an era of massive information overload. We are bombarded constantly.
It's a defense mechanism, really. Once your brain gets trained to think and claim evidence and reasoning, the actual structure of how you perceive information fundamentally shifts.
How so?
Well, when you scroll through a social media feed and see an influencer making a wild health promise or a politician making some big environmental statement, your brain will automatically trigger the filter.
Right.
You'll stop and ask, wait, what is their actual claim? Do they have evidence? And does it pass the 4 tests? And are they explaining the mechanism, or are they just trying to sell me something?
It completely transforms you from a passive consumer of information into a critical consumer. You stop taking things at face value, you demand the evidence, and you demand the reasoning. It's essentially a cognitive superpower.
A superpower that protects you from misinformation and empowers you to make decisions anchored in reality.
We have covered so much ground today. To wrap this up into a really concise, actionable package for our junior scientists listening, you can distill the entire CER framework down to 3 incredibly simple questions.
Just 3.
Yep. You should ask yourself these 3 questions every single time you observe a phenomenon or run a lab. First, what do you think? That is your claim.
Second, what supports it? That is your evidence.
And third, why does that evidence support it? That is your reasoning.
What do you think? What supports it? Why does it support it? It really is the universal language of scientific discovery.
To the 7th grade life science students and your teacher, thank you for coming on this deep dive with us. We really hope that the next time you see a CER worksheet, you don't view it as busy work. You are being handed the blueprint and the hammer. You are learning the architecture of how to decode the universe.
And before we end, I do want to leave everyone listening with one final kind of provocative thought.
Oh, I love these.
We established early on that all scientific claims are provisional. They are open to revision the second new, better data arrives. Knowing that, what is a scientific fact you believe today that you think might be completely rewritten by new evidence in the next 50 years?
That is a brilliant question to chew on.
Sure.
Keep questioning the world, keep demanding strong evidence, and never stop reasoning.